This is graphing another rational function. It is 8.3, practice C number 7. F of x is equal to the rational function 3x squared plus 2x minus 8 divided by x squared plus 3. And again, I want to encourage you to have next to you your little graphing a rational function step-by-step instructions. So, number 1, plot the x-intercepts. Well, if I'm going to have the intercept of the x-axis, that is going to be where y is equal to 0. So I want to set y, f of x, y, equal to 0. And if I set that equal to 0, I'm only concerned about my numerator. If my numerator is equal to 0, then my function is going to be equal to 0. So let's see if we can factor this out. I have 3x squared plus 2x minus 8. I'll use the Mr. LeBron method, or the surefire method of factoring. 3 times negative 8. 3 times negative 8 is negative 24. What two factors of negative 24 will give me a positive 2? And that would be a 6 and a negative 4. So I can factor this 3x squared plus 6x minus 4x minus 8, because my 6x minus 4x is the same thing as my positive 2x. And now I'm going to group these. So out of this side here, I'm going to pull out a 3x, and that's going to mean it's multiplied times x plus 2 minus, well, I'm going to pull out, I guess I'll pull out a 4, and that is also going to be times x plus 2. Don't forget that I had a minus sign. You can barely see it, but stick it right in there, a little minus sign. So that minus sign is going to make this 8 positive. That's why it's x plus 2. So if I continue to factor, I'm going to have 3x minus 4 times x plus 2. Well, that means that x is going to equal positive 4/3 on this one here and negative 2 over here. So I'm going to go back to my graph, start plotting points already. I'm going to go to negative 4/3. So what's that? That's like a little bit more than 1, huh? So negative 4/3 right there, and positive 4/3. There goes Mr. Jenkin again, messing up bombing LA. Negative 2 and positive 4/3. Those are my two x-intercepts. Of course, I wrote them down properly. So as not to make you wait, I cloned the page. Your the calculations to find the x-intercept are on page 1, which I will print for you. And I want to go to the second step, which is to plot the y-intercept. So number 2, what's my y-intercept? Well, my y-intercept is going to be where x is equal to 0. So can I plug 0 in for x? What am I going to get? I'm going to get 0, because with my x squared, and I'll make that 0, plus 0 minus 8 over 0 plus 3. So my y-intercept is going to be negative 8/3. Well, that's that. That's almost 3, right? So let's go put it in red so you can see the color scheme. So it's almost 3, so I have a y-intercept right there. Let's write that down on our screen at negative 8/3. And let's erase this. You can keep on going from here. So the next question is, what is my vertical asymptote? Those 3 vertical ASYMP, that's good abbreviation. Vertical asymptote. Areas where the domain can't exist. Where the domain can't exist is where the denominator becomes 0. So what I'm going to do is I'm going to set x squared plus 3 equal to 0. Let's solve that. X squared equals negative 3. Take the square root of both sides. I'm going to get x is equal to plus or minus radical 3i. Well, radical 3i is a complex imaginary number, and it doesn't exist on the graph. That's telling me there is no vertical asymptote. If all I get for my value of x to be 0 is an imaginary number, I don't have a vertical asymptote, because all the asymptotes have to exist on the Cartesian plane. And negative 3i, anything with i, does not exist on the Cartesian plane, does not exist in our graph. So our vertical asymptote is none. Vertical asymptote? None. That's nice to know. Well, how about a horizontal asymptote? Here's my function. So let's erase that there. Three kinds of issues with horizontal asymptote. There are rational fractions that are proper, and that is where the power of x that is light is on top of that is heavy. For example, x to the 1 over x to the 2, that would be a proper rational function. And when you have a proper, the asymptote is x is equal to 0. I'm sorry. Y is equal to 0. Y is equal to 0. Our x-axis, if we have a proper rational function, our x-axis is going to be the asymptote. But we don't have a proper rational function. We have a rational function where the powers are equal. It isn't light over heavy, it is equal. So, if it's equal, when I have equal and the powers are equal, all I need to do is take the leading coefficient of the highest power of the numerator and divide it by the leading coefficient of the highest power of the denominator. So that would be 3 over 1. I'm going to have a horizontal asymptote of y is equal to 3. If you want to know what to do when you have an improper rational function where the power on the top is higher than the power on the bottom, go to the problem that I did, number 5, because that was that circumstance. But in this case, I'm going to have a horizontal asymptote at y equals 3, so let's draw that in. Horizontal asymptote, y equals 3. All right, so number 4, we had our horizontal asymptote. Let's write it there. Horizontal asymptote is at y is equal to 3. So I would like to find out, as kind of a corollary to my horizontal asymptote, is will my function cross the horizontal asymptote? Remember, you can never cross a vertical asymptote. I don't have any vertical asymptotes in this graph. But you can cross a horizontal asymptote. It's a good idea to know where that might happen. So what I'm going to do is I'm going to set my original function, which I pulled down here, equal to 3. Because the equation for my horizontal asymptote is y equals 3. The equation for my original function is 3x squared plus 2x minus 8 over x squared plus 3. So let's find out. Let's first multiply both sides by x squared plus 3. X squared plus 3. that's going to cancel out my denominator. And I'm going to have 3x squared plus 2x minus 8 is equal to x squared up 3x squared plus 9. It's beginning a little interesting, actually. My 3x squareds go away. I have 2x minus 8 is equal to 9. That gives me 2x is equal to 17. X is equal to 8.5. Wow. So it is telling me that I am going to cross my horizontal asymptote at 8.5. So here's 8.5. So somewhere over here, there's actually going to be a point on my graph. That's very interesting. We'll come back to that in a minute. And when we do come back to it, one of the things that we're going to show is how, even though it crosses the horizontal asymptote still guides the end behavior of the graph as x approaches infinity and x approaches negative infinity. Even though it's going to cross the horizontal asymptote is still going to be a guide for that. So let's plot, on point number 5, plot a few points in each region. I don't have a horizontal asymptote. I do have a y-intercept. I don't really have much of an idea what this graph is going to look like. I have kind of an idea because I see my point here, and I see a point there, and I see that I'm going to cross the horizontal asymptote there. I'm still not quite sure what it's going to look like. Let's put in another couple points. And I took the liberty of sticking this into my calculator already, so it's my y1. And I'm going to graph it for positive 5 and negative 5. So I'm going to go alpha, f4, y1, and I'm going to do it for the point 5, and I get 2.75. So at x equals 5, I'm going to have a point of 2.75. So 5 and about, so that's, it came out a little bit lower than 3. I wonder if I can move that. I don't think I can. So with the magic of video editing, I just readjusted my horizontal asymptote. So I'm looking for the point 5 and 2.75. So here's 5 and 2.75. So I can kind of see what the right side of this thing is going to start to look like. And I'm going to do the same thing for negative 5. I want to see what the point would be at negative 5. So I'm going to go like this, negative 5 parentheses. And just a little bit greater than 2. So at negative 5, I have it just a little bit bigger than 2. So this is beginning to take shape here. It's going to look some kind of like a seagull, like a bird with wings, like a V. So I think it's going to look something like this. I'm going to sketch it in and get rid of that thing there. Okay, so I'm going to sketch it in. I think it's going to look something like this. It'll cross there, but it's going to stick with that horizontal line. And this way here, it's not going to cross the asymptote. I know that because I calculated it and I didn't see it crossing on the negative side. I think it's going to look something like that. So let's take a look. Since I already plugged it into the calculator, I'm going to go zoom 6. And sure enough, that's kind of what it looks like. Now, I'm a little bit off, though, because if I'm looking where the thing dips, this point right here is not the minimum point of the graph. And the only way to find out the minimum point of that graph would be to graph it on your calculator and do a little min-max thing. But, you know, for the purposes that we're looking for, it's okay. It's close enough for government work. I think that low point would probably be a little bit over this way here. The other thing I did was I put in our horizontal asymptote of y equals 3, and I'm going to turn that on, and I'm going to go zoom 6 again. And so you can see there's our graph, and there's our horizontal asymptote. Now, if you want to turn off the video right now, you can, but if you're interested in knowing a little bit more about the horizontal asymptote and how we can possibly cross it, I'm just going to describe that a little bit right now. What I did was a couple of things. I'm going to show you on the calculator. And I'm going to change the window here. I'm going to change the window to my x min at 0, and I'll leave my x max at 10, and I'm going to leave my scale at 1. But I'm going to make my y minimum 2.5, and I'm going to make my y maximum 3.5. So I want to zoom in on this area here where I have my horizontal asymptote of y is equal to 3. And I'm going to make the scale of it 0.5 so I can see even a little bit better. Now I'm going to push graph. And you can see, here comes my 3.0. You see it crosses right at that one spot, right at 8.5. But even though it crosses, it doesn't just continue to go up towards infinity. It's going to stay hugging right around 3. And I'm going to show you that in 2 different ways. One is I'm going to change my window, and I'm going to go x min at 0, but I'm going to make x max 1,000. So we're going to look out to 1,000, which is, a pretty big number for this function. And I'll make the scale by 10, so you can see it a little bit more clearly. But I'm still going to zoom in on that area right around the horizontal asymptote. I'm going to graph it. There's our graph, and here's our horizontal asymptote. Now you can't see it very well. You can't see any of this V portion there, because that's all happening between what? Like between -10 and +10. So every little niche on the graph here is 100. So we're not really, you can't really see that very much, but you can see that our graph is popping up above our horizontal line a little bit, and then getting closer and closer and closer to 3. So it's going to stay right there with 3. The other thing that I did was I went second quit, and I did, let's do alpha F4, and I want to evaluate this function when y is equal to, let's do 100. What is it when y is equal to 100? When x is equal to 100? It's right about 3. And if I go alpha F4, and I do it again, I want to evaluate it when x is equal to 1,000. Well, it's even closer to 3. And if I did one more time, alpha F4, I'm going to do it, I don't know, 10,000. And close it off. Again, it's just getting closer and closer to 3. So you can see that 3, y equals 3 is the end behavior of this graph, even as far as it goes out infinity, even though it does cross it there at 8.5.